Well, good morning. Today we are going to go very, very deep into power series. And the question came up last day. I think Lisi asked, is that are functions
Oh
also
my
power
gosh.
series? Oh my gosh.
Oh, sorry. I was talking to my friend. Sorry.
Yeah, Kai, go ahead and mute yourself. Unless you want us to all hear the conversation. That might be a little bit embarrassing. Anyway, the question came up, are all functions power series? And the answer is actually yes. I can make up a power series. I can just give you a summation. It's a power series. There's nothing special about it. I can do stuff to it. But our interest today is, how do I make an e to the x, a sine x, a log x? How do I make that into a power series? And that's a very, very special thing. And that's the most useful part of all of what we're doing. So I'm going to start off with a definition. Analytic. Now, in a lot of math classes, you don't see this until maybe differential equations, which is unfortunate because we need to know this today because it has everything to do with what we're going to be doing. Analytic has to do with differentiability. Now in Calc 1, you talk about differentiability of functions, and there's 4 types of non-differentiable points. My Calc 1 students learned differentiability probably a month ago. So there are 4 types of non-differentiable points. I just want to remind you because that's where analytic comes from. So for example, if I have y equals square root of x, okay, the domain is all real numbers. No, the domain is all non-negative numbers. So the domain of this is 0 to infinity, but we know the derivative doesn't exist at 0 because dy dx is 1 over 2 root x, and that's not defined at 0. So we say that 0, x equals 0, is a non-differentiable point. It's a value in the domain, but it's not in the domain of the derivative. So it's not differentiable at 0. 0 is an endpoint. Okay. The second type of non-differentiable point, let's do cube root of x. Okay. Something interesting again is happening at 0. This time the domain is all real numbers, but when I take the derivative of this function, okay, x to the 1/3, I get this. And again, the derivative does not exist at 0, but I'm defined at 0. In fact, I'm continuous at 0. In this case, we have a vertical tangent, not an asymptote, a vertical tangent. So this was an endpoint. This was a vertical tangent. Okay, let's continue. There's 2 more. One that we don't generally spend much time in calculus with, and that's the absolute value function. But we know the absolute value function is special. In fact, we don't like it from a calculus standpoint for many reasons. Okay, on one side of 0, this is the line y equals negative x, and on the other side, it's the line y equals positive x. But at 0, I have a sharp corner. I am continuous at 0. So once again, the domain is all real numbers, but no derivative exists at 0 because from one direction, the derivative is -1, from the other is +1. And here we have what's called a corner. Okay, that's the third type of non-differentiable point. You notice I am continuous there, but I cannot take a derivative there. And the fourth and last, probably the most interesting of all of them, x to the 2/3. At x equals 0, does anyone remember what this one's called?
Cusp.
A cusp. You can cut your finger on those guys, so be careful. Like that kind of thing. So again, the domain is all real numbers, but the derivative of this, and by the way, a lot of these look very similar. The derivative, once again, is not defined at 0. The function is defined everywhere. It's continuous everywhere, but it's not differentiable at the origin. So the term analytic has to do with the function being differentiable. And so the way we say it is, in each of these cases, the functions were analytic everywhere except where they were not differentiable. So you are analytic everywhere you are differentiable. So analytic goes with differentiable. And in fact, I'm not even sure why we have different words, except the difference is analytic does not apply to one derivative. Analytic applies to all derivatives. Okay, so let me give you an example of that. Let's start with something fairly simple. If I have y equals, how about, let's say x to the 3/2 power, all right? I know that the derivative of this exists at 0. dy dx is 3/2 x to the 1/2, and that exists at 0. But the second derivative would be 3/4 x to the -1/2, and that x is now in the denominator. So the second derivative does not exist at 0. Analytic means your derivative, every derivative you take forever and ever and ever and ever and ever exists at that value. So although this is differentiable at 0, this one is not differentiable at 0. Therefore, the function is not analytic at 0. What we are interested in is every place a function is analytic. In fact, particularly 0, because 0 is our favorite number to evaluate. So when I'm making a power series, it has everything to do with where the function is analytic. So an easy way to think of analytic is if I took derivatives, if I just took derivatives forever and ever and ever, can I evaluate the derivative at every real number? And if I can't, what real numbers can I not evaluate it at? So it's analytic everywhere I can evaluate the derivatives. It's not analytic everywhere else. And I don't have to fail on every derivative. I just have to eventually fail for it not to be analytic. So we know what differentiable means now. Differentiable means the derivative exists at that value. So analytic means it is infinitely differentiable. I can differentiate it forever and ever and ever and keep evaluating those derivatives. So polynomials, for example, we'd say they're infinitely differentiable because eventually I'm going to get 0, but sine and cosine, e to the x, I can differentiate these forever and ever and ever, and then I can evaluate them forever and ever and ever, and I never get into trouble. But anything that has a denominator or has an even root, I might get into some trouble there. So now, let's consider the following, okay? Consider I have a function f of x. I don't know what the function is. I have a function f of x, and let's say f of x, it's a transcendental function. It's an e to the x. It's a log of x. It's a sine of x. It's an inverse tan of x. But I have a very specific function. My claim is that this function is going to equal a power series. Now, when we say we're going to expand it about C, we can only expand it about C if f of x is analytic at C. That means all of the derivatives of f of x, f prime, f double prime, f triple prime, forever and ever and ever, all of my derivatives have to exist at the value C. That's why we really like C to be 0 whenever possible, but C cannot always be 0, and we'll see that. So that means that f is analytic at x equals C, okay? I'm claiming that there is a power series out there. Well, that makes it easy. If I can say that I'm going to just be able to write this, the question is, these guys, what are those? So here's what we're going to do. We're going to write the power series, and then we're going to expand it and mess around with the derivatives. So consider, first of all, if I expand this power series, let me write the first few terms. Then I'll have a0 plus a1 x minus c plus a2 x minus c squared plus a3 x minus c cubed plus forever and ever and ever and ever and ever. Now let's write the derivatives, a few of them. F prime of x equals what? Well, that would be gone, and now I would have a1 plus 2a2 x minus c to the first plus 3a3 x minus c to the second. And then the next one would clearly be plus 4a4 x minus c to the third plus forever and ever and ever. Now, how about f double prime? I'm just going to do a few derivatives. Well, that would be 0. And now I would have 2a2 plus, bring that down, 6a3 x minus c to the first plus 12a4 x minus c to the second. And I'll just say forever and ever and ever. Oh, let's do one more derivative. We're having so much fun. That's gone. Then I would get 6a3 plus 24 x minus c to the first, forever and ever and ever. Okay. Now here's what I would like to do. I would like to evaluate each of these at the number c. Remember, we just said all the derivatives have to exist at c. So I know f prime of c exists. I know f triple prime of c exists. Okay. What is f of 0? I'm sorry, not f of 0, sorry. F of c. 0, what am I thinking? Well, if I put a c in for x's, every one of these terms is going to be 0. Well, that makes it easy. So that means f of c is equal to a0. Ooh, that's useful. All right. What's f prime of c? If I replace all my x's with c's, then won't all of these be 0? And f prime of c will simply be a1. What's f double prime of c? Well, let's go to this line. Well, all of these guys are going to be 0, and all I'd be left is 2a2. And what's f triple prime of c? Well, let's see, everything after here is going to be 0, and all I'd be left with is, oh, I just realized I have a 20. That should be 24. That's 24a fourth, or a4. Sorry, lost my a there. So this would be 6a3. Now just going to do one more. If I said, what's the fourth derivative evaluated at c? Well, the next one when I differentiate is going to be just 24a4, isn't it? Now here's my goal. I'd like to know, what is the nth derivative evaluated at c? Ooh, boy, that would be really tricky. But look at the coefficients. Where did 24 come from, by the way? Didn't it come from fourth power down, and then I did multiply that one by the third power, and then multiply that one by the second power? Didn't this come from 4 times 3 times 2 times 1? Didn't this one? Didn't the 6? 3, 2.
It's going to be n factorial a sub n.
Does everyone see? Beautiful. That came from 4 times. When I'm bringing down my exponents and decreasing them by 1, it was 4 times 3 times 2 times 1. That was 3 times 2 times 1. That was 2 times 1. 1. Well, then what would that one be? By the way, what is the value of 0 factorial?
1.
1.
1.
Do you guys see it? This is 0 factorial. This is 1 factorial. This is 2 factorial. This is 3 factorial. This is 4 factorial. So William wins the prize today. The answer is n factorial, an. And this, by the way, is one of the most important results maybe in all of Calc 2. And we just figured it out. Remember how I started? I said, let's assume there actually is a power series for my function. I have a function, a very explicit function that I know how to take derivatives of. And think of things that you know, sines, cosines, e's. I have a function. What I don't know is this. We just figured out what every one of these is. Every one of these is this. So now working backwards, I can tell you what an is. If I solve for an, that means that an is equal to the nth derivative of my function evaluated at c divided by n factorial. And that's actually what's going to go right here. So now I can say, if I start with a function f that is analytic at c, by the way, if it's not analytic at c, you're wasting your time because you can't do any derivatives. The majority of the functions you deal with, they are going to be analytic at 0. The ones that are not analytic at 0 are probably analytic at 1. So in reality, the only 2 values you're ever going to use when you're creating your own power series are 0s and 1s. And you don't really so much as choose to say, where am I analytic? And that determines my choice. I can now say any function f of x, if it's analytic at c, is equal to, now I'm going to write it in this form, the nth derivative evaluated at c over n factorial times x minus c to the nth power. This guy right here, this particular power series, this is a power series. This power series that I created by taking derivatives, this is called a Taylor series. and they're kind of important. A Taylor series is not just a power series, it's a power series that was created by taking the derivatives and doing so. So let's do a couple of power series. Let's create a couple of Taylor series. All right, so I'm going to start with e to the x because we did that last day. All right, so let's consider f of x equals e to the x. Now, I can evaluate it any real number because e to the x is infinitely differentiable and infinitely analytic. It's analytic everywhere. But I don't really want to evaluate all my derivatives at 5 or -7. Where do I want to evaluate all my derivatives, do you suppose? For that function? Probably
C?
what?
Oh.
Probably what value of c? Probably
0.
0, because e to the 0 is 1. E to anything else is icky. So
I was looking at the wrong function.
Pardon?
I was looking at the wrong function. I was looking at the Taylor series still.
Oh, I want c equals 0. Simple rule of thumb. If your function's analytic at 0, you want to use 0 because it makes evaluating the derivatives a lot easier. That's usually the case. It's not an absolute, but it's most of the time. So let's do a few derivatives. So f prime of x is e to the x. F double prime of x is e to the x. I bet I can do this all day and not make a mistake. A lot of times folks will say, how many derivatives do you have to take? And the answer is yes. You have to take as many derivatives as it takes for you to see a pattern. Because we're trying to create a summation with a general formula for the AN. I can only do that if I see a clear and obvious pattern. So usually it's probably 3 or 4 derivatives before you can see a clear pattern, although in this case it was a little bit easier. So f of 0 is 1. F prime of 0 is 1. F double prime of 0 is 1. Heck, ... I think it's safe to say that the nth derivative evaluated at 0 is 1. Now, what did we just say AN is in general? We said it's the nth derivative evaluated at c over n factorial. In this case here, what's that going to be? The nth derivative evaluated at 0, we just said was 1. So this is my general coefficient of every term in this particular power series. So now I can say with certainty, e to the x equals the sum from 1 to infinity of this x minus c, x minus 0. You don't write x minus 0, just write x. Now, last day, I told you this was true. I've just derived it for you. And remember last day what I did was I took derivatives and I showed you that the derivative of this power series was itself. That's pretty convincing evidence that it was e to the x, but this is the actual formal derivation. The formal derivation is by doing the derivatives, and you look at this and go, this just wasn't all that hard, was it? This was actually kind of easy. Now, one of the nice things is, if I just go a few terms, this is a power series. This is called a Taylor series. If I just wanted to go a few terms out, that's not a series. That's just a polynomial. So next day, we're going to talk about Taylor polynomials. So if I said, let's just go out 3, 4, 5 terms, then I would have a polynomial that is ridiculously close to this. It's asymptotic. So if I was to evaluate my polynomial, I would get very, very similar values to the if I evaluated this. So I can use the polynomial as an estimator for the function. That's what we do in real life. Okay, so now the next question. You're going to like this. Okay, because e to the x is analytic everywhere, that it has no issues. This is my formal mathematics now. You got to e to the thing, or thing can be anything you want it to be, is equal to anybody want to make a guess what goes here?
Thing to the end.
Thing to the end. And this is one of the single most important results, like I said, in all of Calc 2, because that's the thing that's going to allow us. I mentioned last day solving the impossible problems, coming up with an antiderivative of something that can't be integrated and things of that nature. Because of power series. See, I can integrate this because I can integrate this. This is a polynomial. But what if I took something that couldn't be integrated, but I have the power series? I can integrate the power series. So what is e to the x cubed? What is e raised to the x cubed? Anybody want to try it? That's my
X to
thing.
the third to the n.
X cubed to the n. Can I clean that up? Rules of exponents. What would that be?
X to the 3n.
X to the 3n. Isn't this still just a polynomial? This is a polynomial where I have constant x cubed, x6, x9 forever and ever and ever. Why is that? Why do I even care? Good luck integrating that thing. Integrating this piece of cake. By the way, this is the dominant theme of a lecture next week. So we'll get into that part heavily on the calculator and technology aspects, but you're gonna like that. We're gonna take problems that cannot be done and do them anyway, and get ridiculously accurate answers in just a few steps. When I say ridiculously accurate answers, I mean going 3 or 4 terms and having 15 decimal place accuracy. Guaranteed. I mean, it's absurd how high a level of stuff you can do with cheap calculators if you understand the mathematics behind it. So this right here is a very powerful statement. So how does that help me? All right, well, here's what I'd like you all to do. I want you all to take just a minute, and I want you to find a power series How about for x to the 6th power times e to the x cubed? I want to find a power series for this, because maybe I'm going to need to integrate this at some point. Maybe I'm going to need to manipulate this, evaluate this, whatever. I want a power series for this. How can I do something so crazy? Well, let's walk through it. You just told me that the power series for e to the x cubed, you just told me that was this, correct? So that means that this is x to the 6th times now the question, when it comes to a sum, n cannot be in and out of the sum. N is the only thing that is changing. But remember, the sum of a constant times the function is a constant times the sum. Constants can go in and out of the sum. Since the only thing changing is the n, then technically is x to the 6th a constant or a function? If the only thing changing is the n. Anybody?
It's a constant.
It's a constant. And that means that if I can move it there, then this just became this is equal to this. And this just wasn't that hard to come up with. Isn't that cool? Oh, that is just so cool. So a Taylor series is when I create my own power series using derivatives, all of them evaluated at a particular value. And that particular value is the value I'm expanding about. 0 whenever I can make it work. Now, why can't I always use 0? Let's take something like the square root function. It's not analytic at 0, so I can't use 0. What about the natural log function? It's not analytic at 0 either, so I'm going to use probably the number 1. There's a lot of functions where if the x shows up in the denominator in some capacity, I probably can't use 0 in the same way. Let's do the cosine function, because that's a really good one. I don't like this. Okay, I'm going to do the cosine. The sine is the exact same work, not the same result, but the work that we do for the sine looks just like the work we do for the cosine. So let's consider f of x is the cosine function. Now the cosine function and all of its derivatives, which are just sines and cosines, I can easily evaluate at 0. So I don't want to choose pi or pi over 2 or something else. That's ugly. I want to use 0. Okay. So I probably need to take a few derivatives to see a pattern. So f prime of x f double prime of x, f triple prime of x, fourth derivative. So clearly, every four derivatives, this is going to cycle. I think that's kind of obvious. So now what about f of 0, f prime of 0, f double prime of 0, f triple prime of 0, f fourth derivative is 0? Because once I establish this, it's just going to be the same forever and ever and ever. Cosine of 0 is 1, sine 0. Negative cosine of 0 is -1, and then back to 0. Now I'm to cosine of 0. What do you think the next few are going to be? Anybody want to try? 5th, 6th, 7th, 8th. What are my next sequence of numbers, do you think? What's the next one going to be? Oh, 0, then
-1.
-1, then 0, then +1. Does everyone say it's going to continue forever because this pattern will continue? So that means my power series, remember the power in general, the a n x minus c to the n. Remember, this is a0 plus a1 x minus c to the first plus this is what we have. So in this case here, I'm going to have a0 plus a1 times x minus 0 to the first power plus a2 times x minus 0 to the second power plus a3. Oh, I'm sorry, lost. Sorry, that should be over 1 factorial. Almost lost those guys. Then plus a4, which should just be 1 in this case. Okay, again, reminding ourselves. My c is 0, and all of my derivatives are either going to be 0, 1, or -1. So based on this pattern right here, and by the way, if you want, put 0 factorial. There's nothing wrong with that. That's still 1. This is going to be what cosine looks like. Do you notice anything about the odd degree terms? Anybody?
They're all 0.
All of the odd degree terms are 0, which makes it a little bit trickier to write. Only the even degree terms are going to be non-zero. Now, if I look at the even degree terms, they alternate sign. Oh, 1, -1, 1, the next one's -1. So because of that, we can easily establish something. And the way we're going to say it is, don't think of it as x to the n, think of it as x to the 2n. Because if n is an integer, then 2n we know is an even integer, 2n plus 1 we know is an odd integer. So think of this as being, okay, that would be x to the 0th power, x to the second power, x to the 4th power. So my x is definitely going to be the 2n, okay? Notice the factorial goes with the exponent, doesn't it? So my factorial is going to be 2n factorial. Now, the other part, I'm starting with +1, and then my next term that I use is a -1. Then the next term that I use is a +1. So I don't want -1 to the 2n power. Negative, by the way, what is -1 to the 2n for integers n? Anybody want to guess? -1 to the 0, -1 squared, -1 to the 4th.
1.
That's just 1. That's not what I want. I want -1 to the n. Now let's do a quick check. When n is 0, I'm -1 to the 0, which is 1, over 0 factorial, which is 1, times x to the 0, which is 1. Okay. Now when n is 1, I'm -1 to the first, which is -1, over 2 factorial x squared. Boom. When n is 2, I'm -1 squared, which is +1, 4 factorial x to the 4th. Boom, and so on. So folks, this is the power series for cosine. It's actually,
Professor, how did we get the 2n again?
oh, because we're only using even values, because all of the odds are zeros.
Okay.
See, here's the problem if I just use an n. How do I get a 0 in there? You said there's no way I can get a 0 in the middle of this. Oh, but by going 2n, this is only considering even exponents. and even factorials, which is what I have. Now, when we do the sine is real similar, except sine's going to be the odd exponents. So the power series for sine looks very similar to this, but instead of 2n, it's going to look like 2n plus 1. And everything else is going to be exactly the same, which is really kind of cool. So this is the power series for cosine. Now, we can do this. We are not going to do this for every single power series, but we can do this for a lot of the power series. I want to do it a different one. Let's suppose, and I'm going to show you why this can be so powerful. Okay. Now, the Taylor series, okay, the Taylor series I'll write it the formal way. What if I only want a polynomial of a particular degree? What if I want this thing to stop? I only want a few terms. Then we say P, I'll use K because I'm using that as my subscript. Pk of X would be the same thing, but I'm going to stop. So if I said P3 or P5 or P11, that just tells me where I'm going to stop. That tells me the degree. It doesn't mean how many terms, it's the degree that I want to stop at. And it turns out that, and by the way, this guy here, I have a really clever name. If this is called the Taylor series, this is called the Taylor polynomial. And you'll find you use Taylor polynomials more than you use Taylor series. Because for a Taylor series, I actually have to see a pattern with the derivatives. For a Taylor polynomial, I just got to take that many derivatives. So if I asked you to find a Taylor polynomial, with 5 terms or 3 terms or 7 terms, that's how many derivatives I have to take. I don't even have to see a pattern. But if I want to produce this, I have to actually see the pattern, and that's not always an easy thing. So here's what we're going to do, and I'm going to show you why this is even relevant. We're going to do this as a form of estimation, which is one of the most powerful tools we have. Now you say, why would I estimate if I can just calculate? Well, first of all, calculators weren't always around. They are now, but they weren't always around. And secondly, we may have situations where we can't do a direct calculation, right? I may give you a definite integral of something that has no antiderivative. Oh, so what do? We use a Taylor polynomial as our estimator instead. So let's consider my f of x. I'm going to do something really simple. Let's say my f of x is the cube root function. And I want to use, and oh, by the way, and I want to estimate, let's say the cube root of, how about 1.2. Now, of course, I can just do this on my calculator, but I want to estimate the cube root of 1.2 using P3. That means I want the 3rd degree Taylor polynomial. So I'm going to walk you through, because there's some language here we're not all particular with. Now, I know when I start taking derivatives of the cube root function, it's going to end up in the denominator. So therefore, it is not analytic at 0, but it is analytic at 1. And the value I'm asking you to calculate is very close to 1. So a good rule of thumb is if the value that you're expanding about, in this case, that would be 1, and the value you're doing your calculation is not very far away, then it means your estimation is going to be really good really early on. If I said, let's expand this about 1, and now let's estimate the cube root of 1,000, that's probably not going to be very accurate, too far away. So here's what we're going to do. Let's first write this as x to the 1/3. Now let's we need 3 derivatives, because the 3rd derivative is going to how we get the coefficient of the x cubed term. So first derivative, second derivative, and then the 3rd derivative would be positive. Okay, so now f of, oh, by the way, we're going to use, if I didn't put that, we're going to use equal 1, because we know all of these derivatives exist at 1. They do not exist at 0. So f of 1 is, cube root of 1 is 1. F prime of 1 is 1/3. F double prime of 1 is -2/9. F triple prime of 1 is 10/27. We now have enough information to finish the problem. Whenever you're doing a Taylor polynomial is asymptotic to the original function. It cannot equal. My third degree polynomial that I'm going to come up with cannot equal the cube root function because that's equal to a series, an infinite. So what we're going to do is an estimation or an asymptotic thing. So here's how we're going to say it. The cube root function is going to be estimated by, oops, not B, sorry. I want to write B for some reason. Sorry about that. Now, let me write over here. The cube root function is going to be estimated by P3 of x, which is first, and if you want to write over 0 factorial, that's okay, plus 1/3 over 1 factorial, x minus 1 to the first power, plus -2/9 over 2 factorial, x minus 1 squared, plus 10/27 over 3 factorial, x minus 1 cubed. A little tight. There's no plus ... This is the third degree polynomial that I'm going to use. Now, clearly we can simplify the coefficients, but what I don't want to do is I do not want to multiply x minus 1 cubed. I don't want to multiply that out, gather terms. No. Too messy. Just simplify the coefficients. So this would be 1 plus 1/3 times x minus 1. -2/9 over 2 would be -1/9. X minus 1 squared. And then here, 10/27 over 6, what would that be? 5/81. And then that would be x minus 1 cubed. Okay. In fact, you know what? Yeah, that's beautiful. Here's what we're saying. We're saying the cube root of x. Now, if you have a graphing calculator and you graph the cube root. If you graph the cube root function and you graph this polynomial close to the number 1, they would look almost identical. But now here's the ultimate. We're going to do the calculation now. I'm going to erase this up here. I need to evaluate this. I'm going to evaluate this at 1.2. So P3 evaluated at 1.2 is equal. I'm evaluating this. So that would be 1 plus 1/3 times 0.2 minus 1/9 times 0.2 squared plus 5/81 times 0.2 cubed. Now let me get out my calculator. So 1 plus like this. So my calculator, I'm leaving it in exact terms. Okay. My calculator says, down, this answer is exactly 2152 over 2025. This is a rational number. You just change those to 1/5. Okay, that's exactly what it is. So that means I can now say with certainty, if I did it right, that the cube root of x can be estimated by this. And here's what Taylor polynomials in general will produce rational numbers. I'm estimating an irrational number with a rational number. Now, I'm pretty sure I did it all correctly. Yeah, I have a really good warm fuzzy feeling that I did this correctly. Can we do better than that? How can I be sure that I didn't totally mess this up? Pretty sure I did it right. I could have lost a negative sign, made a bad calculation. Anybody got an idea? How can I be sure that I just, sorry, that should be, sorry, cube root of 1.2, sorry. Can I use this thing, maybe? Let's calculate the cube root of 1.2. I think you all were thinking that. The cube root of 1.2 is approximately 1.0626, I'll throw a few decimals, 58, dot, 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 dot. All right. Now, 2152 over 2025, which is a rational number. This number is approximately 1.026716, blah, blah, blah. So when I'm looking at my numbers, wow, they don't disagree until the fourth decimal place. That's pretty good accuracy. They agree until, I mean, if you look at it, they differ by less than 1/10,000th. That's pretty good accuracy. What if I wanted it to be more accurate than that, though? I want more decimals to be correct. Any ideas?
You do more
What?
more
Derivatives?
power.
More terms, yeah. In fact, if I go one more term, I probably gain 1 or 2 more decimal places of accuracy. That's how it works. It's not that you gain 1 per term. No. Why? Because these factorials are going to get so big so fast that they'll be, okay, now I have 2 decimal places. Now the next one, I'm 3 decimal places better. The next one, I'm now 4 decimal places, because the distance between terms is going to grow as these denominators get bigger. So one of the beauties and the power of what we're doing is that we can do tremendously accurate estimations. Now, the word estimation doesn't even imply accuracy. Accuracy is because I checked it versus an actual calculator and said, my gosh, those are ridiculously close. In fact, if I only needed 3 decimal place accuracy, I got the same answer for both, didn't I? So that's kind of a cool thing. So what have you got so far? If I give you a specific function and I tell you what number to expand about, you can all give me the Taylor series if you can see a clear and obvious pattern of the coefficients. And either way, you can always give me a Taylor polynomial by just taking a few derivatives. You notice we didn't even look for a pattern in those numbers. We didn't need to. We just needed to calculate those coefficients. And then when I did, that polynomial there is unbelievably close to this. Squiggles, because it's not equal, it's asymptotic. Think of it like a tangent line, leaving a curve kind of thing. Very, very close together. Now, there's one more concept I want to show you.
Mr. Brown,
Yes.
I think you mentioned this last class, but so the way that the calculators that we have work is that they choose an arbitrary like P sub 10 or something like just a number that's going to give you 9 digits of accuracy.
Okay. It's changed over the years. Advancements have changed over the years because, if nothing else, the sheer speed with which a calculator can do things. It's doing a calculation. This is just doing it light speed. The idea is, if you see like this rolling, imagine this rolling sequence of numbers, you've seen things like that on TV. The idea is when the convergence happens after the last digit on my screen, then it will display number. I can easily ask a question on my cheap calculator that it will take it 2 or 3 seconds. It will be a delay, and then it will give me a number. And it's kind of crazy. It usually involves things like logarithms and stuff, because logarithms converge much slower than other things. And the idea being your calculator is doing things so much faster than we can imagine, but it's not doing it instantaneously. That's the difference. Now, if I ask it to add 2 numbers, it's literally doing it instantaneously. But if I ask it to do e to a power or the cosine of a number, that's not instantaneous, because that has to be calculated. And the calculator, how is it calculating? So in a lot of cases, it's calculating by using series. It's just doing it at such unbelievable speed. Now, one of the problems, especially the earlier calculators had, was the problem of analytic functions. There was many years that if you gave negative input to a calculator, regardless of the question, if the input was negative, you often got an error message, even when you knew there was nothing wrong with it. If you asked a cube root of a negative number, and the reason I know this, if we were sitting in a calculus class today, all of us, and I said, everybody do the cube root of -1 on your calculator, I guarantee you 1 or 2 of your calculators will actually say domain error or input error, or give some error message. Cube root of -1, what are you talking about? Yeah, there are still calculators now, crummy calculators, of course, that still do not deal with negative input. The technology is still really archaic. So over the years, people have had to do things, because there are questions you can ask your calculator. A really good graphing calculator, right? You should never see a vertical asymptote. But a really good graphing calculator, if you ask a question where the vertical asymptotes happen at irrational values, it'll generally connect the dots because a deficiency in the calculator. And what I mean is, if I ask you to do something like this, there's two vertical asymptotes, one at positive root 2 and one at negative root 2. And so we already know that the calculator, it should look something like this. Let's see. So on one side, I think I'm going to do this. Let's see, on the other side, I think I'm going to do this. Here, when x is 0, I'm here. And the calculator at some point is going to do something like this. It's actually going to connect them. You say, wait, it's going to cross the vertical? Yeah, all technology will cross the vertical asymptote. Why? Because the pixels are rational numbers. When you have, every 100th or every 1,000th or every 10,000th, you're going to do the calculation. Those are always rational increments. Your asymptotes are at irrational increments. I mean, it's just simple common sense is going to connect the dots because there's no irrational input. It can't, not in the graph. So there's still some limitations. I can do this on any calculator, get it to connect over a vertical asymptote by just using irrational values. But that's not something that should be a deal breaker. As long as you understand when technology is limited, as long as you understand it, you know how to work around it. For example, if your calculator doesn't do well with negative input and you're doing the cube root of a negative number, do cube root of the positive number and slap the negative on after the fact. I mean, there are little obvious things like that. Now, we know something about a geometric series. That's the next thing we're going to deal with. We know, and usually when we say geometric, we know we always say A1 R to the n, but I'm going to change it. I'm just going to call it R to the n. But I'm going to start at n equals 0 now. This is actually the most general form. You say, wait a minute, I thought a geometric, there was a first term, the A1. Yes, there is. But I want you to think of factoring the A1 out of the problem. Okay, so if it's A1R to a power, every term has the same A1. So anything that can be written in this form, this is 1 plus R squared forever and ever and ever. We know this is a geometric series. This is a geometric series where the first term is 1 and the constant ratio is R. So we know this is going to be first term over 1 minus R. Always? That's a question. Is this always true? Are there restrictions?
R has to be less than, absolute value of R has to be less than 1?
Yes. This is equal as long as the absolute value of R is less than 1. That's critical. If I said, let's let R be 3. So 1 plus 3 plus 9 plus 27 plus 81 is going to equal 1 over 1 minus 3. 1 over 1 minus 3 is negative, by the way. I don't think that's going to work. No, the R has to be smaller than 1. We derived that several weeks ago. This is a very important identity, but it's the back and forth. So the flip side is if I have something that looks like this, so let's suppose I said the following. Here's my f of x. I want you to write this as a power series. Can you write this as a power series? Oh, by the way, without taking any derivatives. Well, I thought I had to take derivatives. Do you really need to take derivatives? Isn't x my r? So what's the power series? Anybody?
X to the n.
X to the n. As long as I still have to throw in that disclaimer, by the way, that part doesn't change. Oh my God, that was so easy. I have something that looks like this. This is equal to this. I don't have to do any work because we already had it for the geometric, but I do need to throw that disclaimer. Now, here's what I want to do next. I want to manipulate things that look like this so I can figure out what the power series looks like. And every time, and by the way, here's what we're doing. We're taking the fact, this is a fact. We proved this. If I have something that's geometric in nature, I can go back and forth with that condition. So now I have something that looks like a function. Well, all I'm doing is replacing r with x. I'm not really doing much, but then I can do this as long as I throw in the disclaimer. So I want to manipulate this and see how, what I can do. So let's do a couple of simple examples. I want to write we're going to do the same thing each time. We're going to write whatever I write down, we're going to write it as a power series. So what if we have something like this? I have 1 over, how about 4 minus x? That doesn't look like this. Well, not yet. I'll give you a hint. Whatever you're dealing with, you must make it look like this. It has to look like this. I got a 4 on the bottom. How do we make it look like that? Well, could I do this? Should I make that my first step? So if I do that, what am I left with? 1 over anybody?
R or X over 4.
X over 4 or 1/4 x. You'll find 1/4 x is actually going to be easier. But yeah. Now, do you all agree that algebraically these are the same? So what do I do with the 1/4? I don't do anything with the 1/4. It's not going anywhere, but it's not part of the power series. Does everyone see that this is my R? This is of the form 1 over 1 minus R. So what must go right here? 1/4 x to the nth power. Now, are we done? Can we walk away yet?
Don't we have to still make the disclaimer?
Well, yes, that will be the last step of every problem. But I'm talking about for this power series. Are we done, or is there more we can do? Well, generally speaking, I said before, the form of a power series, this is the form of the power series, meaning that the exponential term, the thing involving x to a power, and the coefficient should absolutely always, without exception, be separated. I'm not done. This is not a power series. I don't have x to the n. I have something times x raised to the n. It's not a power series until the x to the n stands alone. So that's what I mean. I'm not done yet. Everything I said is true, but we're definitely not done. So how about if I did this? Is that correct so far? Rules of exponents, is that correct?
Yeah.
Yeah.
This is a constant. Kind of looks like that one there. Can I move this into that? I have a fourth on the outside. Can I just move it in and add 1 to the exponent? Yeah. So there's 2 ways that I could write this, and I'm going to show you. I can write this as 1/4 to the n plus 1 times x to the n, or I can write this. That's probably not the way you would see it in a solution. You're more likely to see it like this. Are these the same thing? If you stare at that, you go, yeah. And now if I did a ratio test or something, this one's probably a little easier to deal with, by the way. There's my answer. It's right there. This is the power series that this represents. Now the disclaimer. But where do I go for the disclaimer? By the way, there's a couple ways you could do it. You could do the ratio test directly on that. That's absolutely correct, but it's not the easiest way. No, the easiest way is right here. You said this was your R. And you're correct. Therefore, I just need the absolute value of this to be less than 1. So here's my disclaimer. What goes here?
4.
4. Now, 4 is called, I'm going to give it a new definition, a new term. The radius of convergence is 4. 4 is a constant. 4 is called the radius of the convergence. And I want you to think of radius as being, I want the same amount in each direction. Kind of like a circle, except I'm on a number line. And that's the same term we used when we did like epsilon delta proofs in Calc 1. And, it's called the radius. The radius of convergence is 4. The interval of convergence, slightly different. the interval of convergence, I'd start with this. I'd then write this. And so I'd say the interval of convergence is the interval from -4 to 4. This is the interval of convergence. This is the radius. You like radius better than interval because radius is just a number. I don't have to do any work. Now, normally, once I found the interval of convergence, if you remember last day, didn't we also now have to check the endpoints? You remember that? That's why you don't love interval, because then you got to check the endpoints. Do I need to check the endpoints in this problem?
No.
You're right, but why?
If x is 4, then the denominator is 0.
No, it's actually simpler than that. Aren't we saying this is a geometric series? We're going from here to here because we're saying this is a geometric series, because this is geometric. And a geometric series cannot converge at the endpoints. Ah, see, last day when we had to test the endpoints, it's because we were taking something that was acting geometric. It was acting like it was asymptotic to geometric, but it wasn't exactly geometric. Therefore, there was still the possibility it could converge at the endpoints. But a purely geometric series cannot converge at the endpoints. This is geometric. That's why we're able to do this. Therefore, I do not need to check the endpoints. Yes, you are correct that if I put a 4 in there, that's undefined. That is true. But if I also do the whole ratio test, I'll find that, to stay less than 1, it's simpler than that. It's just simply that this is geometric. So if you're asked for radius, radius is that number right there. Radius is not 1. No. It's the absolute value of x is less than 4. So the radius is 4. 4 is the amount I want in each direction on the number line to get my interval. So you go from radius to interval. Okay, so interval, I give you an interval. Radius, I give you the number that I use to create my interval. So most of you should like radius better because it's less work. All right, let's do another. These can get kind of crazy and fun and just ridiculous all at the same time. So let's do one that's ridiculous. How's that? I've got x squared over 3 plus x. Now, normally we would say, whenever you have a quotient and the degree of the numerator isn't smaller, you're supposed to do the longer synthetic division first. That would be true if I wanted to take a derivative of this. That'd be true if I wanted to integrate this. That'd be true if I wanted to graph this. But I want to find the power series. So I actually don't want to do the longer synthetic. I actually want to work with this as is. Now, what did we do in the last problem? To get a 1 here, we first pulled out the 1/3, if you remember. Okay. And I did this. But I still have an x squared on top. I don't like the x squared on top. So can I factor out the x squared also? Yeah. So how about now x squared over 3? Okay, is that legal? Yeah, I haven't changed it any. But there's still something that's not quite right. Can anybody tell me what's not quite right about the last statement? We haven't made an error, but
Addition?
it's
In
an
the
addition. What
denominator?
do I need it to be 1 minus. Oh man, how am I supposed to make that 1 minus? How the heck do I make that 1 minus? Like that. Am I breaking any rules here? No. No, I'm just taking what's in front of me. We just said algebraically, this is absolutely identically equal to this always. I now have it of the form 1/1 minus r. And that's exactly what I needed. But now that r is going to be negative, and that's okay. In fact, you're going to find that happens about 50% of the time. So what I've got now is x squared over 3 times the power series. And what's going to go here? -1/3 x to the nth power. We'll do our disclaimer at the end, but let's get the power series correct first. Now, the fact that I have a negative here, that means this is going to be alternating. That's it. That's all that means. I got this stuff out here, so we'll worry about that last. In fact, if you want, pull them apart so you don't make these have to fit at the same time. So this is now, how about if I wrote this as -1 to the n over 3 to the n? Is that legal? Everybody stare at that for a minute. Are these the same thing? -1/3 to the n, is that -1 to the n over 3 to the n?
Yeah.
Yeah. And I want to do this because I want to leave the -1 to the end. I want to leave that alone. I don't want to touch that for the rest of the problem because the 3 has nothing to do with that. Now I can work these guys into here. Still -1 to the end, but now what's my exponent on the 3? Three to
N
what?
plus 1.
Well, that's on the bottom, that's on the bottom, so that'd be n plus 1, x to what power?
N plus
2n, n plus 2.
Well, rules of exponents, that's where I would add them. So that would be n plus 2. This, you know what, I don't know that you could improve upon that. I think that's probably the cleanest form you could write that. Some people will say, well, should I pull this completely out? You don't have to. This is the coefficient. Now the disclaimer. This might be a little trickier. Well, what's my disclaimer? That -1/3 x in absolute value must be less than 1. And that's the same as saying the absolute value of x is less than what?
-3.
Careful, absolute value can't be less than a negative. It's tricky. What's the absolute value of -1/3?
1/3.
1/3.
That negative's inside the absolute value. By the way, if it makes it easier on you, tell me. Am I saying the same thing? Are these saying the same thing?
Yes.
Yes, but you wouldn't say absolute value of -3, you'd just say 3. Oh, so my radius is still 3. So how is this different? Because these are alternating. If that had been a minus, these would not be alternating, but my radius would still be a 3. And the 3 comes because of that 1/3. Wow. So this form of finding a power series, most people like because, first of all, there's no calculus, there's no derivatives. This isn't even complicated, but the number of problems that I can answer from this point of view, I can actually generate all sorts of power series of complicated things just by using this. It's really, really neat because now you can say, well, what if I integrated this? I'd probably get a logarithm, or if I differentiated this, I'd get something else. The relationship between different power series through integration and differentiation when I'm using stuff like this, it's endless how many different things you can do. It's kind of cool. All right, we're going to stop there in terms of the material. Okay, I got in through everything I wanted to get in. Now we have an exam on Wednesday. Let me grab this schedule real fast. Mostly because I can never remember what's on it. The first exam was the first 7 lectures. This exam is the following 8. So this exam is everything from lecture 8 through lecture 15. Okay, so the first quiz on this exam was the limits and L'Hopital's and that kind of stuff. So the last, make it easy, the last exam ended with integration and all of our integration techniques. This material started with limits. That was our first lecture. All the crazy limits and the L'Hopital's rules and all that. And then we went from limits to sequences to series. Okay, so our exam goes through then the alternating series, which was what you turned in. It's what you turned in today. Sorry. Look at this. Okay, so there's no mystery in terms of what you're doing. Taylor series, power series, all that stuff. That's obviously exam 3 material. So the way the exam is structured, I just want to make this really obvious. I've given you a lot more questions than you have to do. And so you have choices because the way the test is broken up, there's going to be a section of problems that are just limits. There's going to be a section of problems that are just improper integrals. There's going to be a section of problems that are just sequences. There's going to be a big section of problems that are series where you're asked about convergence. And in every case, I will typically put 2 or 3 on a page. And the only rule is you can skip things, but you have to do at least 1 problem per page. Because in other words, you can't skip all the L'Hopital's. I've given you 3, you only have to do 1, but you have to do 1. I've given you probably 3 sequences, but you have to do 1. Can you do them all? Of course. What you can't do is skip all of them. So I think I've given you over 20 questions and you're going to end up doing like 15. That gives you a lot of wiggle room. You're looking at one and going, I'm not very good at that one. Skip it. but the list of skip-its can't be really, really long. Now, I've thrown extra credit in there like I always do. It's an extra challenge, but the extra credit only comes from L'Hopital through alternating series. In other words, it comes from the exact same material, just a challenge. And the other thing is, and I'll mention this during the exam, but like always, good test taking is you do the minimum number of problems you need to do, get through the test, check those answers. Now, if there's time on the clock, do an extra credit problem. Now, if there's still time on the clock, go back and do extra problems. Okay. And what I mean by that is, if I asked you 3 sequences and you only did 1, but you know you can do more, then you go back and you do an extra one. That's called insurance. Even though I'm saying you're going to do 15 problems, it would be wise to do 16. It's not wise to do 20. No, it doesn't leave you any time to check. But like the last exam, almost every person did way more problems than I asked, and that was wise. Now, the problems that you skip the first time through and then you decide to do at the end as insurance, they're probably not going to be the ones that count, but you never know. There's a problem you felt really good about that you may have completely misinterpreted, but then you did an insurance and that saved the day. Okay, so that's good test taking strategy. So the problems are grouped, they are not random. So the series, they're all together, and there's a lot of series. There's probably like maybe 10 series, and it'll be determine if it converges or diverges, and always give the reason. It converges by the ratio test. It diverges by the limit comparison. If it's an alternating series, and only if it's alternating, do you use the words conditional and absolute in your convergence. So an alternating series can have conditional or absolute convergence. If it's non-alternating, it just converges. You don't state absolute or conditional, because there is no conditional in that case. I guess technically that'd all be absolute at that point. Okay, so this is kind of how the test is structured. Before we take a break, does anybody have any questions on the logistics only?
I have a question. Oh, sorry. Here you go.
Wow, a lot of
Okay, I'll go. Are we allowed to have a note card for?
Yes. Okay, good. That's a good question. So like the last test, a 3x5 card, theorems, formulas, definitions. So what could you possibly have on a 3x5 card? Well, for example, I'll give you an example. We actually have a lot of theorems. People forget. We have a lot of theorems. One theorem would be something like this. Less than 1, converge. Greater than 1, diverge. This is one of the most important theorems we've done this whole semester. That's a theorem. That's not a formula. That's a theorem. That's way more important than a formula. Oh, that's what I do every time I do a ratio test. Right? I'm testing, is my ratio less than 1 or is it greater than 1? By the way, what happens if it equals 1?
Inconclusive.
Inconclusive. It means I probably shouldn't have done a ratio test. It does happen occasionally, but if you did a ratio test and that was the right test to do, you can't get 1. But basically this, because some people inadvertently think 0 in their mind as the comparison or something else. So that's a theorem, for example. Okay, geometric. If I start this at n equal 1, then this would be n minus 1. If we started at n equals 0, then this would be 1. We know this is a1 over 1 minus r if the absolute value of r is less than 1. We know this, we prove this, we derive this. This is a formula. Not a bad one to write down. That's the formula for geometric series. You don't have to memorize that. Now, what you can't do is give yourself a step-by-step instruction manual of how to perform every single test. No. That's open book at that point. But knowing that ratio and root test you're comparing to the number 1, in a limit comparison, you want finite, not 0. And by the way, exactly 50% of all the times you ever use a limit comparison, you should be getting a negative value. And a lot of people will say, well, no, I'm comparing it to 0. No, finite, non-zero. No, when you're getting a limit that's negative, it just means you had a series of negative numbers. Half of your series are going to be negative because half series alternate. Yeah. So what else? There's not a formula so much for improper integration and L'Hopital's, it's knowing how to attack it. So there's less to write on something like that. If you can think of something, by the way, this is always a good idea. So you're working and you're making your formula card and you go, oh, is this legit? Can I write this? Just send me an email and say, hey, can I have this on my card? Usually the answer is yes, but make sure it's only stuff that we're doing, okay? The only integration on this test is the improper integrals. And that's where some of us get in trouble, that we're doing an integration where I have a limit of infinity and we're leaving the infinity all the way through the problem. At the end, I have a log infinity or cosine infinity or something silly and crazy. No, if it's an improper integral, make sure you're making it into a limit problem. If it's just a straight up limit, you cannot use L'Hopital's unless it's of the form 0 over 0 or infinity over infinity. No other form can you use L'Hopital. So a lot of times we have to manipulate it to get it. Now, there is a major theorem that some of you may want to write down. I know you all know it because most of you did a beautiful job. By the way, the quizzes that were turned in overall were really solid. Here's what was interesting. All of the scores were either 20s or 30s, meaning all of the people turned in either 2 perfect answers or 3 perfect answers, not 2 halfway answers. There were sometimes we had a misconception, but for the most part, the answers were either perfect or we had a misconception, but when we did them right, we did them right completely. So I was very pleased. We got the conditional convergence on one, we got an absolute convergence on one, and we correctly did it. You guys were all doing, first consider the non-alternating, make all my conclusions, and then my final answer. So I was really happy. Only one of them did you have to test for conditional convergence. And then there's the nth term test. That's what I'm talking about. The nth term test has 2 pieces, if you remember. So I have something, of this nature here. I have this series here. So the limit as n goes to infinity of an is 0. And by the way, the terms getting smaller technically is they're getting smaller in absolute value because they don't necessarily have to be negative, but it just means at some point, this is true. We just say at some point, maybe the 10th term, maybe the first term, maybe the 1000th term, at some point, all my terms are getting smaller. At some point. It's nice when it happens right away. If I fail either one of these, I diverge, doesn't matter anything else that goes on in life. If I pass both of these, it doesn't mean I have convergence. The harmonic series passes both of these. But in an alternating series, if my non-alternating passes both of these, I'm guaranteed at least conditional convergence. Remember, so that's why this one was so important. If I pass this in an alternating series, but don't start with this, start by checking the non-alternating series. Because remember, if the non-alternating series converged, then you're already done. You have absolute convergence. If the non-alternating series diverges, but also passes this, then the alternating series converges conditionally. And if the non-alternating series fails this, then the alternating series diverges, period. Because your terms aren't getting smaller. Anyway, let's take a short break. We come back, nothing but questions.